Okay, last class we talked about standard states and enthalpy changes, just as sort of a lead-in to doing more stuff with Hess's law. Hess's law being where we could add up the delta H of different reactions, and that would also allow us to change the reaction, so we could add up like a couple of different reactions to figure out what that overall reaction would be. So our standard states, like the standard states in STP, are defined sets of conditions. For our gases, it's the pure gas at 1 atmosphere. For liquids and solids, it's the most stable form at 1 atmosphere and usually at 25 degrees Celsius. The temperature is not something that we'll have to worry about. For a substance that is in solution, it's a 1 molar concentration, so 1 mole per liter of the substance in the solution. Our standard enthalpy change, which has this little degree sign to indicate that it's standard, and the enthalpy change being the delta H, is our enthalpy change when all of the reactants and products are in their standard states. We also have the standard enthalpy of formation, which adds on this little F, the F for formation. And that's our enthalpy change when we're forming 1 mole. So we're always going to be writing these standard enthalpy of formation reactions with 1 mole as the product. That means that we will sometimes have fractional subscripts on our reactants. So this is the one place where, or one of the places where we'll see that. So that can feel a little weird. So that's why I'm emphasizing here 1 mole of our pure compound being formed. Also sometimes called standard heat of formation. For any pure element in its standard state, so carbon as a solid, chlorine gas as Cl2 as a gas, our delta H, our standard enthalpy of formation is 0 kilojoules per mole. We're setting that as our reference state, and we're comparing everything to what is it in its normal natural state. And then this is a table, table 7.5. It might have changed depending on what version of the book you have, that we'll be referencing. There's another table later that we'll also be referencing. So you may need that for some of the calculations. So some examples of formation reactions. The standard enthalpy of formation for methane, which is CH4. We've got carbon as a solid as graphite plus 2 H2s, and H2 as a gas is the standard state of hydrogen. Our standard enthalpy of formation for this reaction for forming CH4 is negative 74.6 kilojoules per mole. So notice that we've got 1 mole of CH4. It's also balanced, which is nice. And we don't have any of the fractional coefficients. We will occasionally see those, or you may occasionally see them. If you're not sure what the standard state of an element is, you can find the form on one of these tables that has a 0. So for example, if we look in the carbon section, carbon as a solid as graphite has a value of 0. That means that it's the standard state. For fluorine gas, for fluorine, F2 as a gas has a value of 0, and so that's the standard state. And then you'll also find various other compounds that show up in there as well. And again, the coefficients can be fractions because we are forming 1 mole of the compound. Another example of this, if we add carbon and oxygen together to form CO, and we want to write a formation reaction for this, we would need to look up the standard state for carbon and the standard state for oxygen. There's several forms of solid carbon, like you can get it as diamond, but the one with the standard heat of formation, or standard enthalpy change of formation, is 0, is graphite. Oxygen's standard state, on the other hand, is as O2, a gas. So we would start out by finding the standard states and adding them in, and then we need to adjust so that it's balanced for both sides. So the equation needs to be balanced, but we can't change the coefficient of the product. So coefficient of the product compound must be 1. So we just change the coefficients in front of our reactants. And in this case, we end up with a 1/2 O2. Normally, this would not be allowed. But in this specific set of circumstances, this is okay. So this is allowed. It's not illegal. We haven't broken any laws. And we could also find the value for the delta H, the standard heat of formation for carbon monoxide in that table 7.5. So a lot of times we'll be referencing back to that. I don't expect you to have any of the values memorized except for maybe some of the standard states, which would just be 0. So like any of our diatomic gases, you would know that those are 0. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, all as diatomics, those would all be a value of 0. Okay, so write some equations for the formation of sodium chloride as a solid and lead 2 nitrate as a solid from the elements in their standard states and indicate the standard enthalpy change of formation. So for our first one, for sodium chloride, the two elements that are going into sodium chloride are sodium and chlorine. And we're forming sodium chloride as a solid. So we could start with Na plus Cl goes to NaCl as a solid. And then we would need to reference what are the standard states for sodium and chlorine. And so we would have to scoot on back and find our standard states for sodium metal. For sodium metal, the standard state is sodium as a solid, pretty easy. And for chlorine, the standard state is Cl2 as a gas. So we can adjust our formula, our reaction, to now have the standard states. So we started off with just the elements. We adapted to incorporate the standard states. And then the last step would be to balance it. Or one of the last steps would be to balance. So to get this balance, normally we would just double the right side, double the sodium, but we need our sodium chloride to have a coefficient of 1, so we're not going to touch that. We're only going to adjust our reactants. We've got 1 sodium on the reactant side, 1 sodium on the product side. We've got 2 chlorines on the reactant side, 1 chlorine on the product side, and so we need a 1/2 in front of our Cl2 to cut that down. So 1/2 Cl2 as a gas goes to NaCl solid. And we would also look up the heat of formation. And that would also be on our table. Or we would have to go find a table that has it. So let's go zoom back to that. So for NaCl as a solid, the value is negative 411.2. And this is in kilojoules per mole. So negative 411.2. Any questions? All right, we also have our lead 2 nitrate. So for lead 2 nitrate, we've got, let me shrink down this other problem. What elements do we have in lead 2 nitrate? We're forming PbNO3, our lead 2 nitrate, as a solid. What elements are in there? Lead. Yep. So we got Pb. What else do we have? What other elements do we have? Nitrogen. And our last element, oxygen. So if you don't have an idea of what the standard states are off the top of your head, just pick out all the elements, separate them out, and you can start there. So starting just with the elements. And then you can go check table 7.5 or whatever values you may be given if it's on an exam, and you'll find the standard states. The standard states, I'm fairly certain, for lead is going to be a solid. Nitrogen and oxygen are both diatomic. So we've got N2 as a gas, and we've also got O2 as a gas, and this is going to PbNO3 as a solid. If you know what the standard states are, or if you've got a good guess of what they are, you could just start with the standard states instead of adding the extra step of going from elements to standard states. And then once we've got our standard states, we need to get everything balanced up between the left side and the right side. Since we are doing standard enthalpy of formation, our product is going to retain its coefficient of 1. We are just adjusting the reactant side. So we need to figure out how many of each of these elements do we have. So I'll just go ahead and balance it here. For our lead, we've got 1 and 1. For our nitrogen, we've got 2 on the reactant side. We've got 1 in each of our 2 nitrates, so we've got 2 on the product side as well. And then for oxygen, we've got 2 on the reactant side. We've got 2 times 3 on the product side, so 6. So we're going to need to add a coefficient of 3 in front of our O2, and that'll get us up to 6 oxygens on the reactant side. And then we will also look up the standard enthalpy of formation. Again, off of that table. So I'm going to zip us back there. Is it on this one? It's not on this one. It's on the other one. I'm going to zip us back to the one that shows up later. Is it on this one? It is on this one. So this is another table. I think it's from the appendix, some table B from somewhere, that's got a bunch of thermodynamic quantities. We haven't learned about delta G standard F or S standard. We haven't learned about either of those things, so we're just looking at the first column, and we find our lead 2 nitrate over here. It's got a value of negative 451.9. So we'll add in negative 451.9 for our delta H, degree sign lowers F, kilojoules per mole. Questions? Great. So here's the other table that we're going to use. You're welcome to take a picture of it. I'll probably be zooming back to it since I did not take a picture of it. Although I probably have it on my phone. So part of the reason we are doing this is so that we can also do standard enthalpy change for a reaction. Because otherwise it's kind of like, what's the point of putting together this basic reaction if we're just going to look up the value in a table somewhere? It's so that we can use those pieces, the reactions that we just came up with, like in the previous example. We can add those to other things using Hess's law to get new heat of formations, standard heat of formations. So we've been doing elements to their compound. You can also flip them. So this is one of our 3 transformations where you can add a coefficient to all of your values, and that also multiplies the delta H by the same coefficient. If you flip the left and the right, it flips the sign on your delta H. So those rules still apply here. So the negative of whatever our delta H value, since this is a formation value, if you flip it, if you make it negative, that corresponds to the decomposition, the opposite of formation. So if we're calculating an enthalpy change for a reaction, so we've got multiple compounds, not just things in their standard states, then we're going to want to decompose our reactants into elements and then form the products from those elements. And so we'll see what that looks like. This is a arguably overly mathy slide, but we'll talk through it. So any reaction can be written as the sum of formation reactions or decomposition reactions for our reactants and products. Our change in enthalpy, standard change in enthalpy of the reaction is the sum of the standard heat of formation values for the component reactions. So for the reaction, our delta H is the sum, the sigma here means sum, of the coefficient for one of the terms times its delta H, standard heat of formation, for one of the products. If you've got other ones, you would also add the coefficient times that delta H. For that, just copy paste as many times as you need. And then we're subtracting from that the sum of the coefficients times the delta H values for our reactants. Same idea, if you've got one reactant, you have one of them. If you've got multiple, you can add them all up together. The negative here is because we are doing decomposition for our reactants. And so this includes that negative flip that we would do otherwise. So our delta H values are flipped or made negative. So we're subtracting instead of adding there. Okay, example time with some visual of what the steps are like. So we've got an overall reaction. We've got methane reacting with O2 to form CO2 and H2O. So we want to add up the delta H's for our products, because that's what the delta H, this thing, standard enthalpy change of formation. This describes forming the products. So we're going to add all those up with their coefficients, and we're going to subtract everything for our reactants. So these are all going to have negative standard enthalpy of formation values. Because they are decomposing. So we flipped them left and right. Reactants have switched with products. And we've got all of our little reactions here. So we've got our standard state for carbon plus H2, which is the standard state for hydrogen, going to CH4. So that's our CH4. And since CH4 is one of our reactants, we have to flip the delta H. So that's our first step here, the decomposition. We're breaking up the CH4, so it's a positive sign here instead of the negative sign that we would have looked up, we would have found in our table. So we'd flip that to CH4, going to carbon, solid graphite, plus 2H2 gas, and that's where we get this positive (74.6 kilojoules). We also have our products being formed. So our CO2 is being formed. We've got a coefficient of 1, so we're just adding one equivalent of the delta H. So this is negative 393.5 kilojoules per mole. And then for our H2O, we've got 2 of them. And so we're adding here, this is the delta H for 2 equivalents of H2O. Because we've got a coefficient of 2. If we were using this really mathy equation that we had earlier, this one, the way that this would look is our delta H standard of the reaction is the sum of our products. Our CO2 has a coefficient of 1. And its delta H value is negative 393.5. With units of kilojoules per mole. And since we've got this sum term here, then we're adding also our second product, which is the H2O. And the H2O's got a coefficient of 2, so this NP is the 2 there. So 2. And it's got a value for its delta H of negative 241.8. Also with units of kilojoules per mole. And that's our sigma NP delta HF term. So that's what this is telling us. Add up the delta H values for the products times their coefficients if they've got them. And then we're subtracting from that the delta H values for our reactants. In this case, we just have our CH4. So 1 times the delta H value for the CH4, which is the negative 74.6. And we only have to do 1 since O2 is already in its standard state. And that is the sigma NR with the standard heat of formation. So that's like what the math would look like if we wanted to use that equation. Questions? You can choose one of the ways to do it. You can do both ways. They're equivalent. One's just a little more step-by-step, and the other is a little more formulaic. Okay. Example time. The thermite reaction, in which powdered aluminum reacts with iron oxide, which is rust, is highly exothermic, and it's this reaction here. Use standard enthalpies of formation to find the standard heat of the reaction, or standard enthalpy of the reaction for the thermite reaction. So we need to figure out what are the things that we actually care about. Aluminum is in its standard state, iron is in its standard state, and so we can basically just ignore those. And if we wanted to do the mathy way, the formula way, we're doing products minus reactants for the delta H values. It's kind of basically what it boils down to. So then we need to jump back to our table and find those. So we're looking for aluminum oxide and iron 3 oxide. So we've got our iron over here. We've got Fe2O3. With a value of negative 824.2. We also have, for aluminum, this negative 1,675.7. So those are the two values that we care about for this second one. So now we can jump back to our problem. So our product is the aluminum oxide. It's got a coefficient of 1, and it's got the value of negative 1,675.7 kilojoules per mole. And then we're going to subtract from that the value for our reactant, which is the Fe2O3, our iron 3 oxide. It's also got a coefficient of 1, and its value is negative 824.2 kilojoules per mole. So this turns into negative 165.7 kilojoules per mole plus 824.2, also kilojoules per mole. Once we take care of our negatives and our ones. We get a value of negative 851.5 kilojoules per mole. Does that seem reasonable? Yes, it does seem reasonable. The only really point of reference that we have is we're told that it's highly exothermic, and we got a negative number here, and 851 seems like a big number. So negative, big number, highly exothermic. Highly referring to big number, exothermic meaning that we've got a negative delta H. A lot of energy is being released. All right, and then one for you to try. This is also using the Fe2O3, and we're also adding another step. So we're starting with 15 grams of iron powder. I'll write down the delta H value for us. Our iron and our oxygen are both in their standard states. So I'll give you a little bit of time to try that. Okay. So the place that we want to start. Any guesses? What is this delta H with the 0 and the F? What is that describing? It's an amount of heat, right? Because it's got kilojoules. So it's saying that there's some amount of heat released. This is the value for Fe2O3. What's important about this delta H value? What are all standard enthalpy of formation values? The thing that I kept underlining and squaring and boxing in. It's for 1 mole. So you might look this up and think, oh, this is the value for the reaction, which is not true. This is the value for 1 Fe2O3. We've got a coefficient of 2 in front of ours, so as simple as it looks, we do have to remember to multiply by 2. So 2 Fe2O3 will have double the delta H. It is relatively simple because our reactants are both in standard states, and so we just have products. So if we're using this standard heat of the reaction or standard enthalpy of the reaction equals products minus reactants, we don't have any reactants, it's just products. But we do have to remember to do that multiply by 2 part. So standard enthalpy of the reaction is negative 1,648.4 kilojoules per mole. And then we can start with our 15 grams of iron powder. So we just did the delta H of the reaction, the standard heat of the reaction, standard enthalpy of the reaction. We also want to calculate an amount of heat. So how much heat is produced from 15 grams of iron powder? So 15 grams of iron powder is going to be Fe. So we're talking about the Fe here. And we need to convert that to moles. So we're going to find the grams per mole. For iron, 55.85. So we've got 0.2685 ... with 3 sig figs moles Fe. How do we convert that into heat? It's not Q equals MCAT. So yeah, so we're going to use the delta H and the 4 Fe. So because we found the standard enthalpy for the reaction, we can convert from mole equivalents, so whatever the coefficient, in this case 4 moles of Fe in would correspond to this amount of heat out, the negative 1600-ish kilojoules. So 4 moles Fe goes in, and 1,648.4 48.4 kilojoules comes out. So multiply by our delta H, divide by 4. And we get a value of negative 110.68 ... kilojoules. We'd round it to negative 111 kilojoules. And depending on who you ask, this is wrong. We didn't do the calculations wrong. What little detail could make this wrong? Huh? Doesn't need to be per mole. We accounted for the per mole bit. So the question asks for heat is produced. The negative sign in front means that this amount of heat is produced. So some might say the correct answer is 111 kilojoules is produced, since that's the amount that's put out. Which is fairly pedantic, maybe. Questions about any of the other parts? Yes?
So let's say we're working with oxygen instead. So basically it's like the heat of reaction, the standard heat of reaction is per mole of the reaction?
Yes, per mole coefficients of the reaction. So 3 moles of O2 in would also produce this amount of heat. 2 moles of iron oxide produced would also generate this amount of heat. For a mole batch of reaction, this is the amount of heat that comes out. That's what the per mole here means. And a lot of the times when we see a delta H value for a reaction, this per mole part is left off. It's just implied that it's there. And I believe we've seen that before. Any other questions from the chapter? Okay.